Now we will come to the last part of this course. Now we are in a situation to compare the AC and DC transmission. Comparison of AC and DC transmission. Now whenever we get into comparison, there is one aspect that is very important, that is cost. The other one is performance. So comparison can be broadly based on cost and the technical performance. Let us look at first cost or economics. Now if I take the cost will first of all include investment cost and the operational cost. So the investment cost is the initial cost that you need to set up the equipment. Operational cost is once the equipment is there and it's in operation, what is the cost incurred. So let us look at the component investment cost. So investment cost is incurred on what? Suppose I take AC or DC. AC transmission line or DC transmission line. What are the different components on which I have to spend or I have to invest? Yeah. Now before that, when I am talking about AC or DC transmission, let us assume that it's overhead transmission line. Okay. So if there is overhead transmission line, the land below the line can't be used for any other purpose. Okay. One has to buy the right of way. So first of all, there is a land required for laying the transmission line. So cost of right of way. Okay. Then what? Yeah, before that, before coming to conductor and insulator, when I say overhead transmission line, they have to be suspended from tower, transmission tower. Okay. Then conductors, then of course insulators, because the conductor is not just connected to the, it's not hanging from the tower. There is an insulator. It's of course hanging from the tower, but there is an insulator between the conductor and the tower. Insulators. Then what? Yeah. Now there are so many things at the two ends. So these things are only for the transmission line. At the two ends, there may be many other equipment. So we will call that as terminal equipment. Terminal equipment. So if I look at the other components, components other than terminal equipment, they are same. Right of way is there for both AC and DC transmission line. Transmission tower, conductor, insulators are required for both AC and DC transmission line. But terminal equipment are different for AC and DC. Okay. So for AC transmission line, what are the possible terminal equipment? Possible. What are the possible terminal equipment? If I take AC network, there are many transmission lines. Okay. I take one particular transmission line, I could have used DC for that. Okay, instead of AC, I could have used DC. Suppose it is AC, what is the terminal equipment? What are the possible terminal equipment? If it is DC, we will come to what are the terminal. See, transformer is usually an equipment that is required if I want to connect generator to the network or load to the network. See, if I take one transmission network consisting of many transmission lines at the same voltage level, there is no voltage transformation anywhere. See, we need transformers for many purposes. One example is, if I want to connect a generator to the transmission network, I need invariably a transformer. Now I am not considering that part here. what I am trying to say is, in a network, AC network, take one particular transmission line. Okay, so it is not necessary that I will have a transformer in any transmission line. Take arbitrarily any transmission line. At both ends I will not have a transformer. It's not necessary. Okay, so and if I want to connect load also, I will not use the load at such a high level, high voltage level. So I use a step down transformer. Okay, now what I am trying to say is, take any network at the same voltage level, take one particular transmission line. Okay, so now if I take the transmission line, what are the possible terminal equipment? See, if I take a long transmission line, a long transmission line, say a 300-kilometer line, what is there at the two ends? Yeah, there is circuit breaker, fine. Yes, circuit breaker is one thing. What else? Yeah, circuit breaker is correct. Yes, what else? Now, what I will do is, I am trying to compare AC and DC. Even if you have DC, there will be a circuit breaker. So, common things I will remove. See, if I have a DC line, I need a transformer and then a converter. Now, before the transformer, there is a circuit breaker. Okay. Now, I will try to just list items which are unique to AC and unique to DC. So, if I take a long, I am giving a hint. If I take a very long transmission line, invariably we need something at the two ends. Huh? Yeah, inductive reactors. Inductive reactors. That is because under light load conditions, it will cause over voltage if you don't have that. Okay, so there are reactors. Now, reactor means inductive reactor. In power system terminology, we use the word reactor to mean inductive reactor. In circuit theory, of course, reactor can be inductive reactor or capacitive reactor. Okay. Then what else? Sorry? Why do we need reactants? Yeah, see, this is normally taught in a very basic course. If I have a transmission line, there is a shunt capacitance. Okay. Now, if I take long lines, there is an effect called what? Ferranti effect. Have you heard of that? So, this Ferranti effect is coming into picture when there is no load. So, when there is no load, the voltage can shoot to a large value beyond the value for which the line is designed, the insulators are designed. Now, it is not only for no load, it can cause problems even under light load. So, to minimize that over voltage, we nullify or at least to some extent take care of the effect of capacitance by putting an inductor. So, the inductor will nullify the effect of capacitor at least to some extent. That is all. So, that is the point. Now, this problem becomes actually very significant when I have long lines. Longer the line, more is the capacitance, more is the Ferranti effect. Okay. Yeah. Any other terminal equipment, possible terminal equipment? Now, you use reactor for avoiding over voltage. At the same time, when there is heavy load, there can be under voltage. So, what one can do is one can put capacitor. See, the point is, at some point I may connect reactor. At some point I may remove reactor and put capacitor. Okay. If you put both, then there is no use. One is having effect of nullifying the other. So, I don't want to load both. So, at one time I can use reactor, for other times I can use capacitor. Okay. Now, these are the two major terminal equipment. Now, let us come to DC. For DC transmission line, what are the possible terminal equipment? Yeah, what are the terminal equipment? See, I take one possible AC transmission line in a network. I want to replace it by DC. I remove AC and replace it by DC. So, what all terminal equipment come there? Converter comes, converter. Then? No, before that. Say converter means, suppose I say 12 pulse converter, okay, it includes transformer also. But to stress that there are transformers also, I will explicitly state transformers. Okay. So in addition to the power electronic circuit converter, we have transformers also. Then filters. So as I said, filters are of course invariably used on the AC side. They are also used on the DC side along with smoothing reactor. So I call all these things as filters. Then just now we discussed about reactive power sources. Reactive power sources. Okay. So now we have seen what is the investment cost due to. Okay. So I just said terminal equipment which is there for both AC and DC, and we have listed what are the different possible components of the terminal equipment. These are all towards the investment cost. Of course, when it comes to operational cost, I mean, what is the operational cost? What is operational cost? Huh? Losses, mainly losses. Okay. So operational cost is losses. Where are the losses? In the conductor due to flow of current, and any other loss? Loss due to current in the conductor, and corona. And of course, one can also say the loss in the converter and other equipment. So we can include of course loss in the other equipment together. So they are very small compared to the loss in the transmission line. The major loss is the loss due to the current flow, I squared R loss. The other loss is the corona loss due to that is dependent on the environment, of course. Okay. Now, if I want to compare the two, so that's our purpose now. If I want to compare these two, DC transmission line and AC transmission line, so suppose I say that there is a fixed distance, whether it is DC or AC, for a given distance, and for a given power to be transmitted. Now, if I look at the investment cost, so for the time being, I will just look at the investment cost. So, if I look at the investment cost, there are two categories. One is right of way, transmission tower, conductor, insulator. The other one is terminal equipment. So, if I take the cost of right of way, transmission tower, conductors and insulators, I will consider terminal equipment later. Oh, not inductor, insulators. Now, which one has less cost, DC or AC? Huh? DC. Now, right of way is dependent on the number of conductors. Okay. So, though we don't get into the details of the design, I mean, one can try to see that the right of way depends on the number of wires that you need, and I mean the less the number of wires, less I mean we need less investment on the tower from which the wires are suspended, and of course conductor materials is also less, and less conductor means less insulators. So, DC is less expensive. So, okay, let me write it as this is less for DC than that for DC, AC. Now, when it comes to cost of terminal equipment, now without even getting into the exact values of the cost, we can make a statement about the cost of terminal equipment. Which one? I mean, which one appears to be expensive? DC is expensive, right? So, you need so many things. Okay. So, without even knowing the values of the cost of different equipment, we can easily say that DC is more expensive here. Okay. So, this is less for AC. So, if I plot a graph, okay, so I will plot a graph. Where on the abscissa I have transmission line length, and in the ordinate I have the investment cost. Okay. So, I will use say red for DC and say blue for AC. So, I need to plot the curve of investment cost for AC and DC as a function of transmission line length. Now, when I say the transmission line length is 0, if I say transmission line length is 0, say if it is actually 0 for in the case of DC if I have back to back, okay. Now, what is the cost incurred for DC when the transmission line length is 0? It is only on the terminal equipment, So, at 0 length I have something here, I have some non-zero value for the investment cost because it is on the terminal equipment. Now, as I increase the transmission line length, then how does the investment cost vary as a function of transmission line length? Say the other costs, say I have considered already one cost, that is the terminal equipment cost. The remaining cost, right of way, towers, conductor, insulator, they are proportional to line length. So, it is actually a straight line with a positive slope. So, it is like this. Now, if I take AC, how does the investment cost vary as a function of transmission line length? So, here also it is dependent on the right of way, conductor, insulator, tower. So, all these are actually proportional to the transmission line length, but the slope is for AC more, slope is more. So, the slope is like this. So, I have, now I do not extend it to till the investment cost axis, because in the case of DC it makes sense because there is a 0, yes. Slope for DC is? Oh, sorry. Sorry. Yeah, I made a mistake. Okay, both are straight line segments. This is okay. Now, the point is, even if I extend this straight line segment till the investment cost axis, the intersection is lower than that for DC, because the terminal equipment cost is actually less for AC compared to DC. Is that okay? Now, what do these two curves say? The total investment cost. So, there is one particular value of transmission line length below which AC is less expensive, and beyond which, or if I take any length greater than this, then DC is less expensive. Okay. So, this is called break even distance. Now this is I mean dependent on the system, dependent on the voltage level, power level. So based on all these things, one can actually get a range of break even distance. It is between 500 and 800 kilometers. This is between 500 and 800 kilometers. Of course, I am talking about only overhead transmission lines. For overhead transmission lines. So in practice, it's somewhere within this range, 500 and 800 kilometers. Okay. Sorry. Yeah, I have drawn this for a general voltage level. What I am saying is, we can arrive. I mean, typically it is between 500 and 800, which is dependent on the voltage level, the power level, and so on. Mainly, it's voltage level and power level which decides this break even distance. Voltage level, yeah. See, voltage level is hundreds of kilovolt. See, when you come to DC transmission, it's hundreds of kilovolts. Power level is thousands of megawatt. You are talking about what? Your question is, what is the voltage level? That is irrespective of this. Yeah, irrespective of this, the voltage levels are similar to the voltage level of AC transmission. This was something which we discussed long back. When I say thyristor valve, why do I say valve? Why not just thyristor? We have to connect. We don't have thyristor for that voltage rating. So we need to connect many things, many thyristors in series to get the required voltage rating. Okay. So the voltages are in the range or of the order of hundreds of kilovolt. Okay. So the break even distance decides whether, so depending, so distance is given to us. So if the distance is below break even distance, we go for AC. If it is above that, we go for DC, as far as economics is concerned. Now let us do a comparison based on the performance. So if I take technical performance, now when it comes to performance, actually DC has many advantages over AC. So let us look at the advantages of DC transmission over AC transmission. Yeah, whenever we talk about DC, invariably there is a converter, there is a power electronic circuit there at the rectifier side and the inverter side. Okay. So there is some control that is possible in a DC transmission line which is not there in AC. So in AC, the amount of power flow, or for that matter the amount of current flow, is decided by Kirchhoff's law. Okay, there is no, in a conventional system there is no control. There is a mesh network, and the amount of power and current that flows in a wire or in a particular transmission line is decided by Kirchhoff's law. That's all. The utility does not have any control over the amount of power that is flowing in a particular transmission line. Okay. So the major advantage is there is control over amount of power transmitted. So this is just a comparison of DC transmission and conventional AC transmission. Okay. Of course, there is possibility of control in AC if we bring in power electronics there. We give a special name for that, FLACS, flexible AC transmission system, means use of power electronic circuits for the purpose of control in AC transmission line also. Okay. Now when it comes to AC system, always the amount of power is restricted by stability. So you may be familiar with an undergraduate notion of stability, where you would have studied SMIB system, single machine infinite bus system. What is the maximum amount of power that can be transmitted? There is a power angle curve, which is a sine curve. The theoretical maximum occurs at delta equal to 90 degrees, such things. So there is a limit. So that limit is actually the stability limit. It is not the thermal limit. See, thermal limit means the limit which is introduced due to the amount of current that flows in the wire. So the thermal limit may be much larger. Thermal limit are usually larger because we designed a wire diameter such that the corona is minimized. So for minimizing corona, the wire diameter has to be much larger. So that means the thermal limit is much higher than the stability limit. So we can't use the full thermal limit in the case of AC because of stability reasons. So there is an advantage in DC. Power transfer capability is not restricted by stability. Now, again, the presence of converter will not only help in power control, it will also help in control of the voltage. Now, when it comes to transmission line, the voltage needs to be controlled because there is a sag and a swell. If you are familiar with sag and swell, under light load conditions, we have a swell. Even if I keep somehow the terminal voltage at the desired value, the voltage along the line cannot be controlled all along the line. So there will be a swell whenever there is light load, and there is a sag whenever there is heavy load. So such problems are not there in the case of DC because the sag and swell are essentially due to the inductance and capacitance. So the inductance and capacitance don't have any effect in DC. Yes. It has nothing to do with the sag of the wire. That is always sagging. Okay, I am talking about the voltage magnitude. If I look at the voltage magnitude, yeah, that is another sag. The sag you are talking about is the wire sag. Of course, that actually when there is more loading, the sag actually the sagging increases. There is no swell there. Okay, so when we talk about sag and swell both, we are talking about voltage magnitude. Yeah, that point is also relevant. What you are saying, the wire sag increases when the load increases because there is more expansion due to more heating and due to which the sag increases. Okay. So voltage control is actually complicated in AC. So again, I am talking about the conventional AC transmission without use of any power electronic equipment in the AC system. Voltage control is complicated in AC. Yeah. Then there is one major advantage of DC. Suppose I have two systems. Okay, I have two systems, independent systems. I want to interconnect for sharing of power. Then if I have the option of AC and DC, I can choose based on various reasons. If I use AC, then there is one disadvantage. A disturbance in one system will propagate to the other system through this AC one, to this AC transmission line. On the other hand, if DC is used, the disturbance propagation is actually minimized to a great extent. Okay, so if two systems are connected by DC, DC transmission line, so for all practical purposes we can say that disturbance in one system does not propagate to the other system. Now, there is just one more advantage that I want to point out here. Suppose there is a fault in an AC system. I mean, we clear the fault by relay will sense the fault, and the circuit breakers are given a signal to trip. Okay. Now, in the case of DC, there is a possibility of controlling the converter itself to limit the fault current. Now, such facility is not there in AC. So, fast control of I would say fast control can be done to limit fault current. In DC links. So, these are some of the major advantages of having DC transmission over AC transmission.